give the talk.
Thank you.
A round of applause.
Thank you. Does this microphone work? All right, yeah. So I'm Brett. I'm going to be speaking about some work I did at MIT along with Zoe Gong and Michael Carbon on verifying application-specific hardware fault tolerance with programmable execution models. So in the programming languages community, we spend a lot of time talking about software bugs, be they in applications, libraries, compilers, operating systems. However, we don't focus as much on hardware bugs. And hardware bugs are unfortunately very real. So for example, as of September of 2018, Intel has released approximately 175 issues with their 6th generation processors, including one in which cache performance monitor events may be inaccurate, and another in which the processor may hang or cause unpredictable system behavior. But these aren't just theoretical errata. We've seen hardware bugs in practice. On the consumer side, Intel Skylake bugs cause PCs to freeze during complex workloads. And on the Jaguar supercomputer, researchers have found that uncorrectable errors occurred about once every 24 hours in the computer's main memory. So in this talk, I'll be focusing specifically on transient errors, and those can be logical when complex workloads with multiple architectural events happening concurrently trigger corner cases in design, or they can be electrical, as increasingly smaller transistors are more sensitive to physical variation in the fabrication process, or they can even be environmental, where cosmic rays can cause bit flips. But what if we decide to just let these errors happen? In Leto, we allow developers to permit errors by allowing them to specify a hardware execution model that introduces them. So here we show a single event upset error model in our language, in which a single error may cause an arbitrary result in a multiplication. So first we define a Boolean upset flag, which tracks whether or not an upset has occurred. Next, we define the reliable multiplication operator with standard multiplication semantics. And this takes two real numbers, x1 and x2, and ensures that after running, the result is the product of x1 and x2. And finally, we define the unreliable multiplication operator. The when clause of an operator guards its availability at runtime. And in this instance, the operator is only enabled when the upset flag is set to false. The modifies clause states that the operator in its execution modifies a model variable, and in this instance, it modifies the upset variable. And then lastly, the ensures clause sets upset to true and leaves the result unconstrained, thus permitting the execution to evaluate to any possible value. Uncertain computation is nothing new in computing. We see it in machine learning, animations, robotics, and much more. And so thus accepting transient hardware faults isn't much different. It just simply means reframing results that don't fit the traditional computational model, not necessarily as wrong, but rather as different. And these faults can manifest themselves in many different ways. They could, for example, produce an inaccurate result, or they could produce correct results just too infrequently, or they could produce completely invalid results or crash, or in the worst case, do something nefarious. So the natural next question is, well, how do we program on uncertain hardware? How do we express important correctness properties? How do we characterize approximate execution? And how do we reason about these programs to ensure that the desired properties hold? The solution is new programming methodology and supporting languages to address these challenges. There are multiple techniques one can use to mitigate hardware fault, one being replication, to simply repeat the computation until the executions agree with each other. Another is to make the computations themselves checkable, to have easy ways to validate that the result is acceptable. And the last method, approximate computing, is to accept the errors and to reason about them. That last box in the bottom right shows an assertion, a relational assertion in our language Leto, asserting that after the addition, the difference between ZO, or Z in an original error-free execution of the program, and ZR, or Z in the relaxed execution that may experience errors, is bounded above by E. A developer can leverage some or all of these techniques to achieve application-specific fault tolerance, in which the developer uses knowledge of the underlying application to either detect and correct errors or to bound them to an acceptable degree. This graph shows the convergence time for the Jacobi method, which is an iterative algorithm for computing the solution to systems of linear equations from an initial estimate solution. The x-axis is the iteration of the computation, and the y-axis is the Euclidean distance from the true solution. This graph shows two execution traces, one which executes without error in red, and the other which experiences error in blue. And the Jacobi algorithm itself is naturally self-stabilizing. And intuitively, this is because an error in the current solution vector at any given iteration is akin to restarting from a new initial estimate point. However, the extra number of iterations to convergence is bounded logarithmic logarithmically in the magnitude of the error itself. And thus, developers can use application-specific fault tolerance mechanisms to bound the magnitude of error and thus the impact of errors on the convergence time of the algorithm. And specifically, developers can use Leto to specify and verify these bounds on error magnitude. And I'll go into how we do that in a bit. We've built Leto to enable you to specify and verify application-specific fault tolerance mechanisms. Some of the key features and challenges of developing Leto are relational semantics and assertions, automatic verification through forward symbolic checking, and invariant inference for reducing annotation burden. We evaluated Leto against 4 self-stabilizing algorithms under 5 execution models. Leto itself takes as input an execution model and a program in the Leto language. Then it performs invariant inference to add additional loop invariants to the developer-specified set. And it does this in an iterative process of generating candidate invariants using built-in templates and either accepting or rejecting the candidates with an SMT solver. Then it passes the program augmented with additional invariants to the verifier, which discharges the constraints to an SMT solver, and then Leto either accepts the program, at which point the developer is guaranteed that all assertions and invariants hold at runtime, or Leto rejects the program and attempts to provide a counterexample. Now, I'll use a vector product implementation in the Leto language to showcase some of the important features of the Leto language. And I'm focusing on vector product here because it's an important component of many of our benchmarks, including the Jacobi example that I just talked about. So this vector product takes a vector x and a vector y, both of size n, as parameters, and simply just multiplies them element-wise, storing the result in the result vector. Now say we want to modify this example to detect and correct a single event upset in the computation. In the body of the loop, we have duplicated the element-wise computation. We detect errors in this case when D1 and D2 differ. And as our execution model permits only a single error, we can detect all errors with this scheme. In the body of the conditional, we correct the detected error by simply repeating the multiplication. We denote that operators are to be performed according to the developer-provided execution model by appending a period after them. At the top of the slide, you can see a property definition. And properties are hygienic macros that enable reuse of verification conditions. This macro takes a vector x and a size n and asserts that all elements from index 0 to n are equal across the reliable and the relaxed execution traces. And once again, xo refers to x in the original reliable execution trace, while xr refers to the x vector in the relaxed executions that may experience errors according to the execution model. The top of the function contains a relational precondition mandating that n, x, and y are equivalent across both program executions. X here is syntactic sugar for the x in the original execution equals x in the relaxed execution. We've also added a relational loop invariant asserting that the result vector must be equivalent across both executions from index 0 up to index I. Loop invariants behave exactly like loop invariants in traditional verification schemes, in that they must hold both before the entrance of a loop and after each loop iteration. And lastly, after exiting the loop, we verified that the result vector is equal across both executions. And the takeaway from this really is just that this starts to get really non-trivial when you start to think of double events and independence, and Leto helps people, developers, to reason about these types of faults. One alternative to the total detection and correction of errors I just talked about is to make this whole thing approximate. Here we show a single event upset error model in which a single error may cause an error with magnitude relative to the magnitude of the true multiplication. First, we define erel, which represents the relative error of the computation. Next, we define upset, which once again tracks whether or not an upset has already occurred. And next, we define the reliable multiplication operator with standard multiplication semantics. And finally, we define the unreliable multiplication operator. And this operator is only enabled when an upset has not occurred and both x1 and x2 are non-zero. Modifies clause specifies that it modifies the upset variable. And lastly, the ensures clause sets the upset to true and dictates that the result of the multiplication is within erel% of the true result. We're going to use this relative error model now in tandem with 2 additional vector product implementations, both of which place an absolute bound on the result vector, thus deriving an absolute bound from the relative error bounds of the execution model. Both these implementations use the same constants and properties, so I'm going to introduce them now. The max constant is the maximum magnitude of any element in the vector, in the input vectors. The eps constant is the absolute error bound. And the property bounded diff simply states that the error magnitude of every element in eps in X is bounded by EPS. In this implementation, we bound the error by placing bounds on the inputs. We've added a new requires clause stating that the magnitude of every element in X and Y are bounded above by max. And note that this is not a relational precondition, as indicated by the use of the requires keyword rather than requires are, and as such, it holds over both execution traces. At the top of the loop, we perform the multiplication. At the for loop, we perform the multiplication unreliably and use the relational invariant that the error in every element in the result up to index I is bounded above by EPS. And lastly, at the end of the loop, we know then that the error in every element is bounded by EPS. And this effectively verifies that the developer set the max element correctly from the last slide with respect to their relative error specification to achieve the absolute bound that they desired. So that's if we wanted to ban certain inputs. But in this version, let's say we don't want to do that, and instead we want to perform a dynamic check to ensure the difference between the result vectors satisfies an absolute bound. We achieve this by first removing the static bound on the input vectors, and then adding a check that checks whether the result is large enough such that an error could have occurred that is larger than EPS. And if it is, then we simply repeat the computation reliably. We don't have to change anything else in this program. So Leto provides developers with the tools to express and verify application-specific fault tolerance mechanisms. And I just demonstrated this on the vector product implementation using dual modular redundancy for total error detection and correction, and then showed that with just a small number of modifications, I could instead verify statically that the error is bounded, and with only a few more changes, that the error is bounded through dynamic checks. Leto allows specification of arbitrary execution models to verify programs under, and I demonstrated this through the use of an unbounded single event upset model, which I then modified in just a few lines to produce relative error bounds. Our hardware model semantics are as follows. Developers specify custom binary operators as well as custom memory operators. Then at every operator site, the Leto runtime non-deterministically selects an operator such that the current model state satisfies the precondition and such that the output model state satisfies the post-condition. Our execution model is one with a shared structure between two executions with different semantics. In the original semantics, the hardware has standard semantics. And in the relaxed semantics, the hardware has the semantics of the developer-provided execution model. We use a relational program logic for reasoning about code. This logic is similar to standard horse-style program logic, but with the added ability to introspect into variables across the original and relaxed execution traces and compare their values. Our logic also has rules for loops and conditionals, at which points execution may diverge between the original and relaxed executions, as well as rules for reasoning about relational assertions and operator substitution from custom execution model. If you're interested in more detail on the relational program logic, then please do check out the paper. There's a lot in there. Now I'll use the dual modular redundancy product example from earlier in tandem with the unbounded single event upset model from earlier to demonstrate how we use our relational program logic to perform branch pruning, thus improving Leto's performance. Here I have translated the vector product into a control flow graph. If the condition D1 does not equal D2 is true, control flows to the left to the correction step. Otherwise, it flows right to no op. Now consider the four paths execution can take between the original and relaxed execution traces. Here I've shown the execution trace with original semantics with a solid blue arrow and the execution trace with relaxed semantics with a red dashed arrow. One possible scenario is that both executions perform the computation correctly and neither needs a correction. Another is that both perform the computation incorrectly. However, it's important to note that this scenario is not actually possible. It's not possible for the original execution to miscompute D1 or D2 using the original semantics. And so Leto identifies impossible scenarios like these and prunes them and will not go down and verify that path. The third scenario is that the original execution goes left and the relaxed goes right. And again, this is not possible as it's impossible for the original execution to experience an error. So again, Leto prunes this scenario. The final scenario is that the original execution goes to the right and the relaxed goes to the left. And of course, this is possible, so Leto will analyze it. This slide shows a simplified version of the constraints Leto generates to check whether the relaxed execution can take the right path. First, it translates the assume statement at the top directly into constraints. Then it asserts that if an upset did not occur at step 1, then D1R must equal the product of XR and YR. Next, it asserts that if an upset did occur at step 1 or an upset did not occur at step 2, then D2 must equal the product of XR and YR. And then the final constraint is the one of the conditional, specifically that D1R is equal to D2R, and then Leto passes all of this onto an SMT solver, which returns sat, and therefore Leto knows that it must evaluate this path in the relaxed execution because there exists a possible trace that takes it. We benchmarked our system on the following programs. Jacobi is an iterative algorithm for solving linear systems of equations. Self-stabilizing conjugate gradient descent is the standard conjugate gradient descent algorithm with a periodic error correction step every few iterations. Self-stabilizing steepest descent is a standard steepest descent algorithm with periodic error correction every few iterations. And self-correcting connected components is an iterative algorithm for computing the largest connected subgraph of a graph with error correction on every single iteration. Yes? 5 minutes, okay. We verified the programs under the following execution models. We have 3 variants of a single event upset error model. The unbounded model places no restrictions on error magnitude. The additive model places absolute bounds on error magnitude. And the multiplicative model places relative bounds on error magnitude. Our switchable rowhammer model permits large errors on writes and allows runtime enabling and disabling of rowhammer protections. Lastly, our multi-cycle model dictates that once the machine begins faulting, it experiences consecutive errors until the fault resolves. The error characteristics of this model are similar to the switchable rowhammer model. This table shows the verification effort involved in using Leto on our benchmarks, and each row represents a benchmark execution model pair. The columns from left to right are the name of the benchmark under the execution model we verified the benchmark under, the number of lines of code contained in the benchmark, the number of manual annotations we added, and the number of loop invariants that Leto was able to infer. And one takeaway from this is that our loop invariance algorithm significantly reduces annotation overhead. In all but one case, we infer more loop invariants than we provide. The outlier here is steepest descent, in which we had to disable loop invariant inference as Z3 quickly gobbled up all the memory on our machine trying to do it. And this is simply because Leto makes use of undecidable theories in Z3, and sometimes that happens. The other takeaway from this is that half of our benchmarks verify under multiple execution models. And this is because verification and specification effort in Leto ports across models. And one reason for this is just that the applications themselves were designed to be robust to a broad class of errors. And the other is that we've designed Leto with this use case in mind. Leto provides a separation of concerns for programming with distinct execution model and program, whereas alternative systems require the developer to explicitly compose the program with the model to perform verification. This table shows the performance of Leto on our benchmarks. Each row represents a benchmark execution model pair. Columns from left to right are the name of the benchmark execution model we verified the benchmark under, the time required to verify the benchmark in seconds, the maximum memory usage in kilobytes during verification, and the number of Z3 constraints Leto generates. The memory footprint of Leto is reasonable for any modern computer, and our runtime numbers are small, given that in practice these are very long-running algorithms that can take hours to days to converge on large input matrices. And as such, the time to run Leto's verifier pales in comparison to the running time of these programs. Now, you may have noticed that all of our benchmarks are iterative algorithms, and I'd like to take a moment to talk about why that's the case. Firstly, iterative algorithms often lend themselves nicely to self-stability, and intuitively this is because these algorithms start from an initial guess and converge, and an error is akin to a new initial guess. Secondly, previous work focused on localized error propagation of bounded length. So for example, in an image manipulation program, an error may be constrained to only one portion of the image, but in many of our benchmarks, errors quickly. Leto allows a developer to reason about these unconstrained errors. Additionally, these algorithms require interventions or correction steps that restore the quality of the result, and those corrections need to be verified as well. That being said, we believe Leto is also applicable to non-iterative algorithms, as demonstrated by our application of Leto to vector product throughout this presentation, and also because Leto permits expression of many previous approaches for worst-case reasoning about approximate computing. All in all, Leto unlocks the promise of self-stabilizing algorithms, which are otherwise difficult to develop due to the detailed correctness conditions required for error detection and correction, as well as their interactions with the underlying hardware model. Leto facilitates the verification of application-specific fault tolerance mechanisms under programmer-specified execution models. As these proofs frequently relate a faulty execution to a fault-free one, Leto provides assertions that enable developers to relate the semantics of both executions. Leto support for execution models permit developers to convey information about the class of faults they expect their computation platforms to experience. So what's the takeaway from all of this? Well, modern and emerging computation platforms are increasingly vulnerable to error, and Leto holds out the opportunity to develop new, approximate, uncertain, and unreliable hardware with confidence. Thank you. Sure. So the first three examples in this benchmark, they all use a single event upset model. So you're correct; those can only see a single error. However, in our connected components example, we allow an unbounded number of errors to occur. And a large reason we're able to do that is just purely because that has a correction every single iteration, so we're able to reason about that there. Yeah.
Using Rohammer there, are you intending this to generally also be able to survive security attack as part of the underlying that you're focused on?
So that was the motivation for that specific error model, was to be able to try to model Rohammer attack on a system with selective protection of memory. And so that was the intention with that. We haven't looked much at security models beyond that one, but yes, that was the intention behind that error model.
I remember in the Apollo program, one model that was used for sensors can fail, but you need to make a decision, to the entry formula. So they typically triple those computations to the value to agree. The point being that hopefully it's only a single one fail and the other two were correct. But you have whiles there. What if one sensor is bad? They keep all the time the two results were bad.
So Leto, you use Leto to reason about those kinds of worst case scenarios, right? So if you have a model that supports multiple errors and is not correctable with a simple triple modular redundancy that you were talking about, then Leto would provide an execution trace and say, hey, just so you know, this can happen. So Letos would help the developer see, you built your program wrong. Maybe you shouldn't have a while loop there.
So you can actually model.
Yeah, we can model that. Yes.